Good evening, everybody. This Wednesday evening, and I want to open the meeting. Isn't it nice? So, and because our speaker was not telling anything, hi, David, by the way, David stepped up and said, the other David, he wanted to tell us something about his job, right? So you're very welcome to share with us.
Okay, thank you.
You're welcome.
So I have a presentation to share with you this evening about the James Webb Space Telescope. Some of you may have heard of this. It is NASA's newest telescope, space telescope. So about myself, I am at Georgia State University. I'm a senior lecturer of astronomy. I teach solar system astronomy. I teach stellar and galactic astronomy, and I teach a class called Life in the Universe. I am a NASA fellow, and I volunteer for the Jet Propulsion Laboratory at Caltech, and I volunteer for the Applied Physics Laboratory at Johns Hopkins. I give public talks for them locally, nationally, and internationally sometimes. I often work during the summer in the Atacama Desert of Chile at the Gemini Observatory, and hopefully I'll be at the new LSST telescope in the near future. So as a public speaker for NASA, I give talks about like a Perseverance mission, Curiosity mission, and the James Webb Space Telescope is the newest one that I've been talking about. I am, let me pull this up and I will share my screen. Slideshow from beginning. Let's see. I'm a newbie at this. I've never run the show, so please bear with me. Okay, can you see my screen?
Not yet.
No,
Not yet.
So
well, let's see here. Try that one more time. Share screen.
and then the specific
Okay.
Tom have a ghost there. Hey, Tom, nice to see you as a ghost. Looks like a ghost.
Okay, sorry, folks, I'm having a hard time.
Take your time. Take your time.
It's saying allow Zoom to share your screen, open system preferences. I do that. And then, oh, I see it. I need to unlock this. Okay, so I have to quit and reopen. I have to leave the meeting and come back.
Hey,
Okay, so I'll be right.
yeah, that's fine.
Used
But
to
the
be,
worst case, it's really the worst case when you're sitting there, want to make your presentation and then some things like that has happened. Or like me, the last time I couldn't find the Zoom again, you know, and then you're getting so nervous because you cannot get back.
it's good practice. It's good
Exactly.
practice, and
Yeah,
you should all know how to do this because you may all be called upon, like I called upon David, to make a presentation.
mhm. Hey, here we go. You are muted, David. But I can open it up for you. Oh, here we go. That looks good, but you're still muted, I think.
Okay, can you see my screen?
Yes, and we can hear you.
Yes.
Yes. Thank you for your patience.
That's fine.
So this presentation, it's a lot of slides. I'm gonna try to boogie through it. So forgive me if I'm a little brief with some of these topics. If you have any questions, just ask, or you can hold them to the end of the meeting and ask me.
Thank you for stepping up so spontaneous. So don't apologize. Everything is fine.
It's my pleasure. Thank you for giving me an audience for this. This is something I'm very excited about. So they've started they started designing this or conceptualizing this mission in 1995, same year that they launched the Hubble Space Telescope. And the first mission briefing that I attended for this was in 2007. And they said it would just be a year or two until this thing was in space. So every astronomer on the planet has been excited for this, on the edge of our seats, and it's next year. Finally, it launched in December. It's in space now, past the moon. And we're going to be able to observe things that we've wanted to observe for quite some time and answer some of the mysteries that still exist surrounding planetary science, the history of the universe, black holes, a host of topics that are of interest to astronomers. There was, let me get on with it. So we're gonna talk about how James Webb Space Telescope came to be. It's an infrared telescope, so we're going to talk a little bit about why we would use infrared light to study the universe. Let's explore the universe with Webb, and then we're going to learn some of the components of the telescope and the instrumentation of the telescope. Okay, so how Webb came to be. Let's see. Okay, so originally, the plan was that it would be working alongside Hubble, the Chandra mission, and the Spitzer Space Telescope. Spitzer Space Telescope has already been decommissioned. It observed at infrared wavelengths. The Chandra Space Telescope is the one that we use to study active galaxies and black holes. It's still functional, and it observes in the X-ray region of the electromagnetic spectrum. And then Hubble gives us visible light. You've probably all seen beautiful pictures from the Hubble Space Telescope, and it also can get near infrared, a slice of the infrared portion of the spectrum. Okay. So with each additional space telescope, we continue to learn an incredible amount about the universe. These telescopes observe different types of light, offering a unique perspective of objects that are in space. So for instance, in the upper left image here, this is the Crab Nebula. People all over the world reported seeing this in 1054 AD. In China, they saw it. In Europe, they saw it. And it was so bright. It was a star that's supernova. It exploded, and it's still exploding. It's still traveling outward. And they thought that this is how stars were born. You could see it for about 30 days during the daylight. And it was magnificent, must have been magnificent at night. But even during the day, it was brighter than the full moon. So as we study it more, we know more about it. It's the remnants of a supernova, but there is a pulsar in the center of this thing. So a giant star exploded, its core collapsed. It became about the size of Manhattan, okay, between 10 and 20 kilometers across. And where this huge star was spinning, when you make it very small, it's kind of like an ice skater. They bring their arms in and they spin much more quickly. It's the conservation of angular momentum. Well, everything acts like that. So if you have a star that's spinning and then it becomes very small, it spins super fast. And this particular it's a neutron star, but when it sends off pulses of light or radio waves in this case, it's called a pulsar because it pulses every time it passes your line of sight. So we're able to study this with the Chandra telescope. The Spitzer Space Telescope studied Zeta Officii. I can't say Officii. Thank you. So this is a bright star that's obscured by dust, but with infrared telescopes, the Spitzer Space Telescope, we could see through that dust, and we can see the star behind the dust, and we can see that it's sending out very powerful winds, not like winds on Earth, but charged particles, charged protons, charged electrons, and it's sending them out so with so much power that it blows the dust and the gas into a bow shot, kind of like on the front of a boat. When it parts the water, we can see that happening to the gas in space. And then the Hubble has revealed the finer details of the Ring Nebula at the bottom here. And this is the gaseous layers of a dying star about the size of our sun. So this is in our future. This is what our sun's going to do in probably 5 billion years. So we'll talk about that when that happens. And then, then the one in the bottom right, that's the antenna galaxy. So they've used all of our telescopes to look at this. And what's happening is two galaxies are colliding. Okay, so we in this image alone, we can trace the life cycle of massive stars from formation and gas clouds to their afterlife as a compact X-ray source. So, and again, this is a peek into our future. We are on a collision course with the Andromeda galaxy. So in about 3 billion years, we're going to collide with Andromeda and become a much larger galaxy. All the gas in those galaxies are going to collide and initiate new star formation. We'll be called a starburst galaxy at that point, because we'll have a new burst of star formation. Okay, staring deeper into space. Let's see, 1 second. Okay, so you've seen a few objects that are close to Earth. All those images are in the Milky Way galaxy that I showed you a moment ago. But this is looking out further. So this picture was taken in 2014 by the Hubble Space Telescope, and what they did is this is very similar to the first picture that Hubble took in 1995. What they did is they had Hubble look at a seemingly empty part of space, and it just kept for about 10 days. It kept observing. The aperture was open, the shutter was open. It was just taking in more and more light. So what we see here in this seemingly empty part of space is all these images. Every one of these objects, except for about 3, are galaxies. Each of these galaxies have hundreds of billions of stars in them. Even the smallest objects are distant galaxies. So as we use Hubble to look deep into space and deep into the past, we find that space is homogeneous. It's the same. It's full of galaxies, and it's isotropic. It's the same no matter which direction you look in. So when I say we were looking back in time, when we look at galaxies that are this far away, some of these galaxies are 13 billion light years away from us. So that means the light we're seeing from them has been traveling to our eyes for 13 billion years. So indeed, we're actually looking at the past. These could be very different by this point. And the same is true on a local level too. When you look at the sun, when you see a sunset, it set 8 minutes ago. It takes 8 minutes for light to get from the sun to the earth. So this is just that to an extreme. Okay, so capturing faint infrared light. So Webb will match Hubble, but instead of using a visible light, it's going to look at infrared light. And we'll talk more about that in a moment. But because of that, Hubble and James Webb will work together. So we'll be able to take information that we get from the infrared light, and we'll get to layer it on top of image we get with visible light. So to capture light that traveled more than 13 billion years to reach us from when the universe was only hundreds of millions of years old, we need a telescope that focuses on gathering light that had stretched or redshifted over time into infrared light. So at the beginning of the universe, there was ultraviolet light, which was very high frequency, but over time, the universe has expanded. And when the universe expands, the light that's traveling through it stretches out. Okay, we call it redshift, specifically cosmological redshift. So light in this picture, you can see the ultraviolet light, the peaks and the troughs were very close together, but over time, they become stretched out as space stretches out. So you can see where the visible light portion is. So we can see back in time to an extent when we use a visible light telescope, but this light is shifted into infrared, so we're using infrared telescope now, and that allows us to see back further than we could with Hubble. Okay, the early telescope design, it looked different in the beginning. They've learned a lot while they were building this thing. This was built at Goddard Space Flight Center in Maryland. They have the biggest clean room in the world. It was originally called the Next Generation Telescope, and then they changed the name to honor the first director of NASA, James Webb. So they began construction on it in 2002. And you know, the mason jars, they say ball across them. Everyone seen mason jars that say ball? Maybe, okay, well, so Ball has an aerospace division. They got the contract to build James Webb, and they kept running into problems. They run into delays. It just extended the mission. So another contractor bought Ball Aerospace, finished the job, and finally it was launched into space. So why study infrared light? You know, you can get information that you normally can't get with visible light. Visible light is a very small portion of the entire spectrum of light that we can see. In astronomy, when we talk about light, we're talking about radio, which includes microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. So all those are called light. It's because it's easier to say than electromagnetic radiation all the time. But there's a small portion we can see, visible light. So let's see. So in this picture with visible light, we see meerkats and we see a freshwater crocodile, and we can see details about them. We can see their structure. We can see their texture. But when we look at it with infrared, we get a completely different set of information. We can see the heat of these warm-blooded land mammals, these meerkats. We can see the cold-blooded aquatic reptile is just the same temperature almost as the water around him. So we can extend this out into space. Used to, they thought that the Milky Way did not have very many stars in it because most of them are obscured by dust. But when we found out how to use infrared telescopes to look through the dust, we realized that we're dealing with maybe 300 to 500 billion stars just in our Milky Way. So when stars are shrouded in dust, we can see through them with infrared telescopes. We can there's a lot more detail we can get with infrared, and then we can also look at the visible pictures with Hubble and make inferences about the structure of the different bodies that we're looking at. Okay, so yeah, okay, so the electromagnetic spectrum, this is what I was just talking about. Radio, microwave, infrared, visible, UV, gamma ray. We have gamma ray telescopes in space, but they're not very useful for imaging the universe or the solar system. They're more for observing catastrophic events like black hole mergers and things of that nature. But the Hubble Space Telescope, as you can see here, shows us part of the UV, all of visible, a little bit of infrared. It overlaps with James Webb, which gives us near and mid infrared. And unfortunately, the Spitzer Space Telescope is being decommissioned, and it shows us the other end of infrared. But James Webb is much more sensitive, and it's going to give us much more data than we ever would have hoped to get from Spitzer. So this is an example of what I was talking about. These are the pillars of creation. This is part of the Eagle Nebula. These are dust lanes. This is dust clouds in space. And in the first picture, we see it in visible light. It obscures the stars behind them, but then in near infrared and mid infrared, we can see through that dust, and we can even see the temperature of the stars that are behind it. So it unveils so many things that we can't see with at other wavelengths. All right. So exploring the universe with Webb. So when we look back into space, when we look far back at distant galaxies, there's a point that we can't see past. So a fraction of a second after the Big Bang, everything was still energy. As it cooled down, as it became larger, energy, the universe cooled down, and stars were able to begin forming. Those stars assembled into galaxies. The galaxies became more massive. Then finally, before that, the universe was so dense that it was opaque. Light could not travel through it. But eventually, the universe became clear, and we can receive light that was traveling through that early universe. We will never be able to see, well, probably never be able to see what happened in the universe in the first fractions of a second when it was not see-through. But James Webb will help us see as much as possible, all the way back to the first matter in the universe. Let's see, and this, well, okay. So this is just another example of we see distant galaxies. Maybe the light started at a higher frequency there. It redshifted into infrared, so we'll be able to see those distant redshifted light from distant galaxies. Okay. So discovering some of the first galaxies. The picture over here at the right side of the screen is the oldest galaxy that we can see. This image is taken by Hubble, but this galaxy is 13.4 billion years old. The universe is only 13.8 billion years old. And this is the best image I've ever seen of it. It looks like a red smudge. I think this has been doctored up, in fact. Okay, so we would like to be able to look at the stars that make up this galaxy. We don't really know what kind of stars galaxies had in the very beginning of the universe. We don't know if it was dominated by a black hole, if there were supermassive stars that caused the other stars to join the collection. We just don't know. And this image it lacks the proper resolution for us to make those kind of studies, those kind of observations. So this is another thing that James Webb is going to resolve. We're going to be able to look at the individual stars in that picture. Not only that, we are going to be able to look at galaxies in great detail at different distances. So we'll be able to see the oldest galaxy, intermediate galaxies, modern galaxies, and compare and contrast them, and kind of put the pieces of the puzzle together and understand the sequence going from the simple galaxies of the early universe to the more complex galaxies we see today. Okay, another thing is there will be dissecting black holes. Ultraviolet is good, but infrared is better for observing black holes. All right. One of the main targets is a black hole called Sagittarius A star. That's the black hole that's at the supermassive black hole at the center of our Milky Way galaxy. We're going to be able to observe it. Now, you can't see the actual black hole, but you can see things orbiting it. There's giant, they're called accretion disks of matter that move at nearly the speed of light around the black hole. It causes a lot of friction, and it produces infrared radiation. It also produces microwave radiation. So there are several ways that we can study these things. And also it's kind of, there's still some mystery surrounding the jets that fly out of black holes. Now, they don't go out of the black hole itself. They fly out of the disk that's around the black hole. But when too much stuff is trying to fall into the black hole, some of it speeds up and is shot out before it gets there. So James Webb's going to be a good way for us to study this at more detail. And we're also going to use it to study quasars. Quasars they used to think that they were stars, just very, very bright stars. They look like a star that's very close to us. But as we study them more, we realize that most of them are 4 billion light years away, but they still look as big as a nearby star. So what they are is they're galaxies that are dominated by a supermassive black hole in the nucleus of the galaxy that is devouring stars, devouring matter, and causing the whole galaxy to glow. James Webb is going to study those in more detail. Quasar it's short for quasi-stellar light source. They used to think that they were stars, then we figured out they weren't, so they called them quasi-stellar. And we'll be able to look at how stars form, live, and die. These are the same two objects in the Carina Nebula. The nickname for them is Mystic Mountain. So when you see it in visible light, there's some stars that are obscured, and then when we look at it at infrared, we can see right through and see the stars behind the gaseous dusty veils of the nebula. Okay, so when we look out into space, we see giant molecular clouds, and those clouds have all kinds of molecules. We find organic molecules in them. We find water. We find heavy elements. We find everything you would need to build a solar system. We even find hydrogen cyanide in these molecular clouds, which is one of the precursors to amino acids, which make up our DNA. The universe, it's not empty. It's full of matter. Even the most distant reaches of space that are far away from galaxies, they have some hydrogen inside of them. So James Webb is going to let us look at those at greater detail and gain more insight as to how stars form. In a region such as this, we see a bunch of these bright stars. Those are blue stars. They live for a short period of time and they burn up their fuel very quickly. So we know that all these stars formed about the same time. But if we look closely, like in the closest nebula such as this to the Earth, it's the Orion Nebula, when we look at these young stars, we can see solar systems in the process of forming around these stars. And we can see it at all different stages of the formation. So that's how we know, that's how we have our theories of the formation of our own solar system, is by studying other stellar systems. Okay, so the Kepler mission was a mission in which they looked at distant stars and they studied the light that was around those stars, or the light coming from those stars. And when it became dim and then bright again and then dim and bright again, they knew that a planet was orbiting that star between us and the star. So there's thousands of things that they think are planets around other stars. They're called Kepler planetary candidates. James Webb Space Telescope will be able to look at the atmospheres of these stars, of these planets. When starlight shines through, it will illuminate the atmosphere. We'll catch that light with James Webb. And there's a process called spectroscopy that lets us understand what each of the elements are and each of the molecules are in the environment or in the atmosphere of these planets around these different stars. That's how we know if planets are Earth-like or if they may be habitable. So we're using Hubble for that right now. James Webb is going to be much better. So we're going to, a lot of students are going to study. They're going to pick a planet, study its spectra, and they're going to get their PhD for it. There's going to be thousands of them. So it's going to be a very exciting time for astronomers. And this is an example of that. If we were far away from Earth and looking back, we would see that these things, ozone, methane, carbon dioxide, water, that they're absorbing light that's reflecting off of our planet. So we would be able to see, using spectroscopy, that light is being blocked at these wavelengths. So we can tell what our atmosphere is made of from very far away. We can do that in reverse using James Webb to distant planets. We can tell what what their atmosphere is made of. So about the telescope. So yeah, like this is made in Maryland. This is at Goddard Space Flight Center. This is a picture of the largest clean room in the world. This is where they made it. So yeah, the way that they made James Webb, it's an enormous telescope. The heat shield on the bottom of it's the size of a tennis court, and they kind of used origami. They figured out a way to fold it up very small to fit it into the fairing of a rocket. They launched the rocket into space. It went past the moon, and it opened up when it got on the other side of the moon. I was on the edge of my seat. There were 300 things that could fail, and if one of them failed, it's too far away to be fixed. We couldn't go there. We couldn't do anything about it. We'd just be sorry. There's no more science. And it was a $10 billion project, so we weren't going to get another shot at it. So Hubble is a 2.4 meter round mirror. James Webb is a 6.6 meter or 22 foot about segmented mirror. Instead of having a curvature like most telescope lenses, this is made of a bunch of flat hexagons. And what they do, they have actuators under them so they can move them around, and they can move them to where they shape in a curve and act like a lens, like a curved lens. So right now, the James Webb Space Telescope is having to cool down. It has to be maximum of negative 390 Fahrenheit, has to be the ambient temperature of that area of space. And then they have to get all the mirrors lined up to make it have a curvature. So we expect to get, they've already taken some test pictures, but we expect to get some good pictures, some good data in June or July. So again, hurry up and wait. But these mirrors are coated in gold, and the gold is very good for reflecting infrared light. Instruments. So the instruments are NIRSpec, NIRCam, MIRI, and NIRIS. So NIRSpec is the near infrared spectrograph. So that's the one that we can use to sort out what elements are in an atmosphere of a planet, or we can even look at the atmosphere of a star. We've used this technique for a very long time. When they discovered helium, they discovered it using this method, looking at the sun. That's why helium is named after Helios, the sun. So this is they have to use computers to sort out some of the complicated spectra, but every molecule, every element, we can recognize their distinct lines in spectroscopy. In fact, this technology led to barcoding. They figured out that if you could categorize every known molecule or element using light lines and dark lines, that you could probably catalog every item in a grocery store. And so that's why they have barcodes. It's a spinoff from astronomy. NIRIS is the near infrared imager and slitless spectrograph. So it can take the spectra of multiple targets at one time, not just one. NIRCam is the near infrared camera. And then MIRI is the near infrared instrument. Okay. So, when I was telling you that if we were to look through the Earth's atmosphere, we could see that parts of the light were absorbed. So on the left-hand side of the screen, this is what it looks like. These are absorption spectra. These dark lines, those are lines that have been absorbed by something that this light traveled through. And it's the wavelength of the missing light tells us what the mystery element is. So what this allows us to do is we can do two things. If a star is heating up gas, we can tell what that gas is made of. Or if light is passing through cool gas, by the missing portions, we can tell what cool gas it passed through. In astronomy, you can't pick up anything, you can't crack it open, you can't examine it. We're at the mercy of light. Light is the only thing that we can use, so we manipulate it to where we can figure out what we're dealing with, the temperature of what we're dealing with, the composition, everything. There's so much we can tell from light. So Webb's orbit is past the moon. It's a Lagrange 2. So this is a point where the telescope is so far away from the Earth and Sun that their gravitational attraction to it is insufficient to pull it any closer to the Earth-Sun system. But we also have to include the gravity of the moon. So if you see in the picture here, the moon goes one way around the Earth, and James Webb Telescope goes the same way around the Lagrange 2 point. So what's happening is the moon is gravitationally attracted to Webb, so they're mirroring each other. When the moon gets closer to Webb, it's more gravitationally attracted to it. When it gets further away, it's less. So it mirrors it. So there's a Lagrange point on the near side, and there's of the Earth. The word, when we put things there, the Sun and Earth play tug of war with it, and it stays put. And then there's one before and after the Earth too. Those are not as stable, but this is a Lagrange figured this out in I think the 1800s. He's a mathematician, but it's very, very powerful phenomenon. This is what lets us have geostationary satellites that stay over one portion of the Earth. Okay, so James Webb, it has to block out the light coming from the sun, or it can't see these very faint objects. So it has this spectacular shield that shields it from the sun. It has, and then you see the primary mirror system here, the gold portion, and then behind the gold is an instrument wheel. So it can use any of its instruments that you want to use by just turning the wheel and lining the instrument up with the telescope. So if you want to do spectroscopy, you use your spectroscope. If you want to just take a raw infrared image, you can use the infrared camera. And it has antennas to communicate information back to Earth. So this is what it looked like when it unfolded. It left Earth in the fairing of a rocket, went into space, and it slowly went through the 300 or 308 steps it needed to completely unfold. It successfully has hit that mark, and now it's just being collimated and it's cooling. So this is how we talk to it. We have a Deep Space Network. There's one in Goldstone, California. There's one in Madrid, Spain. There's one in Australia. So no matter what time of day it is or where the Earth is in its rotation, we always have a line of sight with a radio dish with James Webb Space Telescope. And that information is sent to the Space Science Telescope Institute in DC, well, by way of Baltimore, Maryland. And then it's put onto the internet. I think it takes about 45 minutes for that whole process to happen. Okay, so Webb's an international collaboration. We have several partner countries in it, although the US did bear the lion's share of the financial responsibility, but we're involved are Austria, Belgium, Canada, Denmark, France, Germany, Ireland, Italy, Netherlands, Spain, Sweden, Switzerland, and the UK. And then there's additional member states in Europe that also contribute to the European Space Agency, which is a partner in this mission. Also, Canadian Space Agency is a partner with it as well. The Space Telescope Science Institute conducts the science and the mission operation from Baltimore, but NASA has the lead overall responsibility. Okay, so like I said, we expect to learn about the early universe, galaxies over time. We're going to be able to see another thing I don't think I mentioned. We'll be able to look at Jupiter, Uranus, Neptune, and Mars, and we'll be able to know more about their atmospheres. And the structure, for instance, Jupiter, the structure underneath the cloud top, we'll understand more about the structure of its atmosphere beneath the visible surface. Okay, so I know that was a lot, but anyone have any questions?
I'll venture one. When the Andromeda galaxy and the Milky Way crash, will that be before or after our sun turns into a red giant?
It'll be before. So about 1 billion or 2 years before that. But fortunately, the stars are so far apart, both in our galaxy and whenever you see a picture of the Milky Way galaxy, we've never been far enough away to take a picture. You're looking at a picture of Andromeda. It's slightly bigger, but we think it's pretty much the same as Milky Way. But all the stars are so far apart that we expect they'll pass right through each other. Just like when we saw the picture of the colliding galaxies in the Antenna Nebula, those stars are not hitting each other. But what is happening is that there's so much available hydrogen that the hydrogen will slam together. Our hydrogen and Andromeda's hydrogen will slam together, and that'll make new star formation occur. So it'll even be full of more stars than just the combination of the two galaxies. The Earth should be fine.
Until the sun turns into a red giant.
That's true. We're going to have to do some work on that. So the general idea is that when the sun turns into a red giant, we'll be very close to it, but it will be cooler. There's some models that show that it could push us away. I don't really understand how that could work, but there are models that show that happening. And then ultimately, it's going to discharge a lot of its outer layers, like that ring nebula picture that I showed you. And what's going to be left behind is a white dwarf star about the size of our Earth. And there's a outside chance that if we survive the red giant phase, and if we can survive the planetary nebula phase, we could end up orbiting a white dwarf. But it's very unlikely, but people have found ways that it could happen.
Well, I won't be around to see it. Although I did see the Magellanic clouds, which I understand our galaxy is interacting with or will interact with. Those clouds that the other galaxies will be incorporated into the Milky Way. Is that, did you have that straight?
Yeah. So the small and the large Magellanic Cloud, they were discovered by Magellan, even though everybody in the southern hemisphere had seen them with naked eye forever. They're Magellans, but they're dwarf galaxies, and that's really cool. You've been able to see them. I have too, and I thought it was breathtaking. It's incredible to look up in the sky and you see a galaxy like the size of maybe a dime.
Mhm.
It's incredible, but those are dwarf galaxies, and they're being towed behind us as we go on our collision course with Andromeda. So eventually, yeah, we'll all come together. Well, I talked a little bit about the fact that space is expanding and stretching out, but that expansive force is called dark energy, and it is not as strong as the gravitational attraction of our local group of galaxies. So even though space is getting bigger, we're still coming on in a collision course, and we'll eventually be just one bigger, oddly shaped, irregular galaxy.
I can truly see where your passion is right now.
Thank you.
It's so impressive, honestly, very nice, very nice.
Thank you. Well, I'm sorry I spoke so quickly. I saw 38 slides and I'm like, oh, I've got to get through this. So if I skipped over anything or if I didn't explain anything well, please ask me. I'll be happy to clarify you. Or if you want to send me an email, I'm happy to.
I have one question.
Yeah.
Do you ever was invited or had the possibility to go to the NASA, so in Clear Lake, like right around here?
Yeah. So when the Challenger explosion occurred,
Yeah.
people put a bunch of money into NASA and they couldn't put it into their budgets. They put it into an education trust fund.
Okay.
So me and 40 other people were selected, and that money was used for part of my graduate education.
Mhm.
So I have a degree in astrophysics, and I worked as a research astronomer. And everyone told me you should teach.
Mhm.
So I applied for this. I was working on my second master's degree in teaching, and I applied for this NASA fellowship, and I received it. So out of 40 people, only 2 of us made it through the program. But what
Wow.
I did is I received 18 graduate credits from Teachers College, Columbia University as a NASA Endeavor Fellow. And I also got to work at some of the different NASA facilities. So I've worked at Marshall Space Flight Center in Huntsville. I've worked at Jet Propulsion Laboratory in California.
Mhm.
I've worked at Johns Hopkins Applied Physics Laboratory. That's NASA facility as well. And one time at Huntsville, they sent me out to the Bonneville Salt Flats to launch high power rockets over a mile in the air with students from Utah State. Paid me to do that. So it was the best experience of my life.
So I truly, I think you have to book the Space Center, because the Space Center is only 20 minutes away from me.
Yeah.
So, and we
Johnson
have an
Space
event.
Center.
Yes.
Yeah, in fact, I know people that work there. And I give, so because NASA paid for my education, every time they ask me to do something, I do it. And every time I apply for something, they give it to me because I guess they want to get their money's worth. So I get to do a lot of cool stuff. And so when I've traveled to South America working for Gemini Observatory, I double dip and I'll travel around the region giving talks for NASA. It was very, well attended. People are very excited about it there.
Yeah,
So
of
I've
course.
several
Yeah.
times.
But what I mean, because we have a Rotary Space Center Club over here, right? So, and that's why the host committee have a tour you can book for the convention, where it will bring you to the Space Center. And there will be some astronauts as well. And the one speaker we had in couple of weeks ago, he will be there too. So maybe you have to book that.
Oh yeah, well, definitely.
That's what I mean, because it will be perfectly fitting to you and to see everything if you was not before, guest of the Space Center in Houston.
So from what I understand, part of that program is going to be based on the New Horizons mission. And I actually did some work on that mission. I've done work on the Van Allen's probes mission. And, so yeah, I would love to go to it.
Yeah, I think you have to go. Really, you have to go, because it's a big tour. It's not only the tourist thing. It's really the deeply tour. You have to book it.
I will.
Yeah, great, really great. I think you should be more here than in Georgia, right? Because to be closer. Very nice. Thank you, David, for sharing.
Oh, thank you for asking me. Yes, I'm happy to.
If you got time for another question?
Absolutely.
Yeah. How long did it take the James Webb to unfurl itself through those 305 stages? And then how long will it communicate with us?
Okay, so it launched on December 25th. I think it was 25th, maybe 26th. I think it's about 1 million miles away. So it took probably 8 days to get there, maybe 2 weeks. And ever since then, it's taken it over a month to open up. So it was. And it will communicate. So they design these things to last for typically a decade or so, but everything that they build, they over-engineer to the point where they surprise us. Hubble's been going since 95, and it's, other than one design snafu that they had to correct, it's been a great telescope, still is.
Well, it sounds like with people like yourself, we're going to get a great return on the investment over time.
Thank you. That's very kind of you. Thank you.
David, I want to thank you for making me feel totally inadequate.
Well, isn't that the truth, David?
Not my intention. But
So David, has this been your lifelong love of astronomy? I mean, has this been, since you were a young boy? How did you
Yeah.
get here?
yeah, so I've always, when I was in Scouts, I loved astronomy. You know, my I'm like most people. I have an uncle who did something for the Apollo space program. I think everyone my age has someone in their life that or knows someone who had something to do with the mission. And then when the space shuttles came about, it was incredible. We were going to be living in space. When I was I remember that show Space 1999. We were going to be able to mine helium on the moon. I always loved sci-fi. I loved the idea of human space flight. I love observational astronomy. It was my thing. After college, I took a few years off. When I bought a nightclub with some friends. I did that for a few years. I was a purchasing agent for a while. I was an insurance adjuster. I've done a lot of things. I always was an amateur astronomer, and I loved it. When I was in my late 20s, I decided, this is what I love. This is what I want to do. I went back. I received my graduate degree in astrophysics. I love doing that work. And then I narrowed it down. Everyone told me, you're a teacher, go teach. So I got the credentials to teach. Actually, I thought I was going to teach high school physics. I was going to school to do that. And then NASA gave me a fellowship at Columbia, and Georgia State University offered me a
Guy
job.
here has
So
got more master degrees and stick at it.
and I have a doctorate in education as well. And what I did is I studied human subjects. I studied the way that my students learn about electromagnetic radiation, and I use different techniques, mostly collaborative learning. And I got a dissertation out of it and defended it. So I've cobbled together a degree in astrophysics education.
Mhm.
So and on my dissertation committee, they had to have astrophysicists and educators so that they could together critique me. But it was,
Did you never thought about to be an astronaut?
I would love to be an astronaut. I think I'm too old, and but maybe they'll give me a one-way trip to Mars. I'll do it. But yeah, if I had the chance tomorrow to go on a one-way mission into space, I would go.
He's like, see ya.
Yeah, I'm out.
You're not as old as James T. Kirk.
Yes. Yes.
That's true. He gave me New Hope, but they didn't. I would have to be. I couldn't pay to go up there. I would have to be paid to go up there, and I think there's probably better candidates that are in better condition. But yeah, that was exciting that James Kirk got to go into space.
But we believe in you, David.
Oh, thank you.
We truly believe in you, and maybe there's a way, but this is again what I said, Andre will join us when we have the event in the Space Center, and maybe you only have to talk with him. Everything is about connections, and you know so much about that, and you are so full of passion. I think that's really something what the people need. They make this step, to be in passion like you are. It's passion. I think all the other classes you teach is not that important, but this is the most important class, right?
Well, so I teach astronomy of the solar system. I teach this stellar and galactic astronomy. So I teach astronomy 1, astronomy 2. So I guide them into it. But then life in the universe, I teach the chemistry, the geology, the biology, the physics, the astronomy necessary to contemplate life on other bodies in our solar system and in the galaxy. So I would take the students on a journey, and I love it. It's my favorite class. And a lot of times it's just an hour-long question and answer talk. And that's so much better than when students are disengaged and doing their own thing. I also work for the Office of International Initiatives, and I facilitate study abroad trips. So I'm planning, I recruit people and I help them develop the trips, and I also try to get students to go on them. So I'm putting together a trip for next year. I'm going to take students for my Life in the Universe class to learn about the anthropology of astronomy. We're going to go to Machu Picchu, which is an ancient observatory. We're going to go to some of the major observatories in the northern Chilean desert and the Peruvian desert. So, and then we're going to go all the way down the coast of Chile. We're going to go to the southern tip, and there's an Antarctic research facility there that is run by a woman who is incredible from what everyone tells me, and she's welcomed us to come there and learn from her. We're going to travel upwards through Argentina. I have colleagues in Buenos Aires that I've worked with, and they're going to show us their telescopes. And then we're going to go to southern Brazil, and then finish up at northern Brazil in the Amazon, so we can learn about biodiversity and extremophiles. It's going to be a 22-day trip, and I'm going to do it every year.
Very nice.
And you know what's awesome is you sound so excited about it.
Yes.
That's the really cool part, is you're really excited about this, and not
am.
all of us have those kind of moments.
I love my job. I've found a job where, like, if I want to do something for NASA, I can do something for NASA. If I want to do something for my university internationally, I can go do it. But bottom line, I teach. I teach those 3 classes, and one more thing I teach. For when people are going to be K through 5 teachers, I take them into the lab for a semester and I teach them chemistry and physics, so that they're more than a page ahead of their students. But I love my job. I get to talk about my favorite subject, and people get excited about it. I have former students who work at astronomical observatories, and I have one student, I took her to a conference in Grapevine, Texas when she was a senior, and she now works for the Space Science Institute that I was telling you about that's going to manage Webb. She called me one time, panicked because she thought she broke Hubble. So every once in a while, I get just this great success story, and that's enough to make it worth it. You know, I mean, there's always a few students who are very excited, and I like to just spend resources helping them out.
But honestly, this is the key. You know, if you do something you are burned for, you are very excited for, this is the only way you can be successful. And you know, and it's not only a job. It's not only, you know, I'm teaching something. It's my passion finally, and that everybody can feel. I'm sure everybody in this Zoom meeting could feel this is your passion. And I think this is important. Thank you, David, for sharing that with us. And I'm pretty glad you are with us in the meeting, and you know, you will lead us the next Rotary year. And so thank you.
Do we need to create like the chief science officer?
Yes.
That's what we need to create.
Yes.
David, the CSO. David, you've certainly inspired me, and as you must do all of your students. So thank you very much for my part for doing this. You've inspired me to get back into to do something about astronomy again. For the past 25, 30 years, I spent a lot of time motorcycling, and that's why I'm with this group. Before that, I was probably 25 years a member of the Royal Canadian Astronomical Society. And before that, with the Okanagan Astronomical Society in the 1970s. One of the trips we did was to go to Glendale, Washington, where there's a small observatory where it was a big deal for us. I think there was a 29-inch mirror at the time, which was a big deal. And that was the first time I laid eyes on the Beehive cluster. And it was like, wow, somebody turned the lights on for me. And it was the most amazing experience. So anyway, thank you for your talk.
Oh, my pleasure. I'm happy that I've inspired you to get back into astronomy. You know, I have a similar experience. The first thing that I ever saw were the moons of Jupiter, and and you go back later and there are different positions. This is what I saw it just like Galileo saw it. That's how he knew that not everything was orbiting the Earth.
Wow.
And it just, yeah, a light came on, just like you said. And it's yeah,
Thank you so
never can
much, David. Thank you so much. And
Okay.
it was so fast that we got to the end of this meeting. And I would like to ask Otto, would you like to lead us in the four-way test for the end of our meeting?
I'm so old, I can never remember it. Of this, of the things we say and do, we say, is it the truth?
Yes.
Is it fair to all
Yes, to all
concerned?
concerned? Yes. 3,
Give it, will
will it build goodwill and better
it
friendships?
better friendships? Is it fair to all concerned?
And
And
Is it fun?
is it going to be fun? Yeah.
Yes. Thank you, guys,
great job, Otto.
for the good meeting.
Thanks
and-
again, David. Great presentation.
Yes.
Absolutely. Take
So,
care.
Uta is going to be, she has an excused absence next week. So I'm going to be your host. Be gentle with me, it's my first time, but I'm going to send a reminder the day of. And I
Great.
look forward to seeing you all there.
Thank you, David. Bye-bye.
Thanks.
Bye.
Good job.
Thank you.